When the fuel reserves in a 4-engine heavy bomber reach zero, the aircraft ceases to be a machine of war and becomes a glider of fixed mass. This is not a negotiable situation, it is a physics boundary. On February 23, 1942, a Boeing B-17E Flying Fortress reached this irreversible threshold. The aircraft was returning from the first American heavy bomber raid on Rabaul. The target was highly defended. The weather was closing in. Port Moresby, the intended recovery field, was still hundreds of miles away, but the remaining fuel was measured in minutes. The pilot, Captain Fred Eaton, held the controls of an airframe identified by the serial number 412446. He faced a calculated decision that would define the location of this artifact for the next 64 years. The crew of 9 men was intact. The aircraft had sustained combat damage, including an anti-aircraft round that punched through the right wing without detonating, but the airframe was structurally sound. The failure mode was not mechanical breakage, but energetic exhaustion. The engines were starving. Eaton did not order a bailout. He chose to retain control of the energy dissipation by forcing a landing. He selected a flat expanse of green below him. It looked like a meadow. It was actually the Agaiambo swamp on the northern coast of Papua New Guinea. This distinction between visual identification and ground truth would protect the wreck for decades. Eaton aligned the bomber with the top of the kunai grass. He committed the 30-ton machine to the surface. The wheels remained retracted. The flaps were set. The aircraft settled into the vegetation. The friction of the swamp grass acted as a geometric brake. The deceleration was rapid but linear. The bomber did not cartwheel, it did not break its back. It slid to a halt in chest-deep water and mud, swallowed by 8 to 10-foot kunai grass, and settled into the anaerobic mud. The crew egressed without a single fatality. They began a 36-day trek to safety. They left the machine behind. The aircraft they abandoned was a rare technological variant. This specific B-17E was equipped with an early production, remote-sighted ventral turret system, an approach later abandoned on subsequent blocks. This system used a periscope sighting station that was often reported to induce nausea and disorientation in the gunner. It was a complex mechanical dead end that was deleted from later production blocks. Its presence on this wreck freezes the engineering configuration to the very early months of the Pacific War. For the next 6 decades, the aircraft remained exactly where it stopped. The Agaiambo swamp denied access. No roads, shallow water over deep mud, and that terrain barrier kept the airframe largely untouched. The aircraft did not get stripped for metal, it simply waited. In 1972, during a RAF helicopter exercise, the wreck was spotted and later visited by Australian soldiers, an interruption of decades of isolation. They found the interior remarkably intact. They found coffee thermoses still stowed in their racks. The press dubbed the aircraft the Swamp Ghost. The name implies a supernatural mystery, but the reality is a procedural case of isolation. The wreck was not a ghost. It was a time capsule locked inside a severe terrain constraint. The existence of the Swamp Ghost presents a specific challenge to the discipline of aviation archaeology. Usually, a crash site is a debris field of shredded metal distributed over a wide impact crater. In those cases, the objective is forensic reconstruction from fragments. Here, the objective is different. The aircraft remained remarkably intact as a coherent airframe from nose to tail, far more continuous than a typical crash debris field. The preservation is exceptional. The problem is not finding the pieces. The problem is the gross weight of the assembly. Recovering a complete heavy bomber from a remote wetland is not a restoration project. It is a logistics problem. The aircraft sits in a location where ground vehicles cannot operate. The mud cannot support a crane. The water is too shallow for a barge but too deep for a truck. The distance to the coast creates a cycle time problem for any aerial transport. The sheer mass of the fuselage exceeds the lift capacity of standard utility helicopters. The engineering team that approaches this site must solve a geometry puzzle. They must figure out how to disassemble a machine that was never designed to be taken apart in the field. They must do this while standing in water that hides snag hazards and sharp obstructions. They must manage the weight of components that require precise handling. They must transport these sections out of the swamp without inducing new structural failure. The gap between the crash in 1942 and the recovery effort is defined by this logistical barrier. The aircraft survived the war, it survived the landing, it survived the elements. The question is whether it can survive the extraction. The preservation is perfect because the trap is perfect. Breaking that trap requires a technical plan that respects the limits of the mud and the limits of the airframe. The objective is to retrieve the history without destroying the evidence. The difference between a crash site and a forced landing site is defined by the rate of deceleration. When an aircraft strikes the ground, the kinetic energy must be dissipated. On a concrete runway, this energy is converted into heat by the brakes and friction from the tires. In an uncontrolled impact, this energy is consumed by the deformation and shredding of the airframe structure. The B-17E, known as Swamp Ghost, survived because the pilot utilized a third mechanism known as soft field landing dynamics. This mechanism relies on the interaction between the aircraft skin and a fluid or semi-fluid surface. When Captain Eaton lowered the bomber into the Agaiambo swamp, he was not landing on a solid surface. He was landing on a suspension of water mud and dense kunai grass. As the fuselage made contact, the surface yielded. This created a profound difference in the structural loads. Instead of a sharp, instant shock, the water and vegetation provided a progressive drag force. The deceleration was spread over several seconds rather than a fraction of a second. The decision to keep the landing gear retracted was critical to this physics equation. If the wheels had been down, they would have acted as vertical spikes digging into the mud. This would have generated an immediate rotational moment, forcing the nose down and likely flipping the aircraft onto its back. By keeping the belly smooth, the pilot allowed the 30-ton mass to hydroplane over the vegetation. The load was distributed across the entire lower surface area of the fuselage and the wings rather than being concentrated on the strut points. The wingspan of 103 feet 9 inches acted as a giant sled. The evidence of this low-energy arrival is physically written on the propellers. In a high-power crash propeller, blades are often shattered or twisted into corkscrews as the engine torque fights the resistance of the ground. On this wreck, the blades are bent gently backward. This deformation pattern confirms the claim that the engines were starved of fuel and were either windmilling or stopped at the moment of impact. The energy state of the rotating components was low, matching the energy state of the airframe. The bomber did not break apart because the environment absorbed the energy instead of the structure. Once the aircraft came to a halt, a new set of physical laws took control. For 64 years, the bomber sat in a wet environment. In most contexts, water is the enemy of aluminum. Moisture usually acts as an electrolyte, facilitating the flow of electrons that drives corrosion. However, the Agaiambo swamp is not a saltwater lagoon. It is a freshwater system with a heavy sediment layer. This specific composition created a condition known as anaerobic preservation. Corrosion of aluminum is primarily an oxidation process. It requires the presence of oxygen to turn the metal into white powder. The mud in the swamp is dense and rich in organic material. At the depth where the fuselage settled, the mud creates an oxygen-starved environment. The heavy fluid seals the metal from the atmosphere. Instead of eating the skin away, the mud encased it. The aluminum formed a thin, protective oxide layer and then stopped reacting. This is the same chemical logic that preserves bog bodies or wooden ships buried in river silt. This does not mean the aircraft is pristine. The environment is dynamic. The water level in the swamp rises and falls with the seasons. This fluctuation created a distinct waterline corrosion pattern on the fuselage skin. The sections that were permanently submerged remained better preserved than the sections exposed to the humid tropical air. The magnesium components, such as the wheel hubs and certain engine fittings, suffered the most. Magnesium is highly reactive, and the fresh water was enough to degrade these parts over 6 decades. However, the primary structural spars and the alclad skin remained structurally competent. The kunai grass also played a dual role. While it cushioned the landing, it also grew rapidly around the airframe. The grass grows to heights of 10 to 12 feet. From the air or from ground level, the aircraft became invisible within months of the crash. The vegetation acted as a camouflage net, shielding the aluminum from direct sunlight and thermal cycling. This thermal stability prevented the expansion and contraction cycles that can fatigue metal joints over time. The survival of the crew and the survival of the machine were achieved through the same mechanism. The soft, absorbing power of the swamp prevented fatal impact forces, and the isolation of the swamp prevented human interference. The trade-off is that the environment which saved the aircraft also captured it. The mud that stopped the corrosion also created a powerful suction effect. The fuselage is not just sitting on the bottom, it is embedded. The sediment has settled into every crevice, creating a mechanical bond between the aircraft and the terrain. To remove this object, the recovery team cannot simply pull. The suction force of the mud on a surface area of this magnitude would exceed the tensile strength of the aluminum skin. If they pull too hard against the mud, the aircraft will tear apart. The preservation is successful, but it has created a heavy and immobile artifact that is now part of the geological noise of the swamp. The physics that saved it in 1942 are the physics that define the challenge of 2006. For a period of 30 years, the status of the B-17E serial number 412446 remained a theoretical entry in a lost ledger. The United States Army Air Forces knew the aircraft had not returned. They knew the crew had survived and walked out. However, the physical location of the airframe was effectively deleted from the map. The jungle canopy and the rapid growth of the kunai grass closed the visual window shortly after the crash. The aircraft existed only as a set of approximate coordinates derived from a pilot debriefing that was decades old. That changed in 1972, when a Royal Australian Air Force helicopter crew visually reacquired the aircraft and logged the site, converting decades-old debrief coordinates into a confirmed location. Identification did not require forensic reconstruction. This was still a coherent industrial object rather than a scattered debris field. The RAAF crew was able to read the data stencils on the vertical stabilizer. They confirmed the tail number as 412446. Inside the cockpit, the instrument panels and control yokes were intact. The identification plates on the radio equipment and the engine blocks matched the build records for the aircraft delivered to the 19th Bombardment Group. There was no ambiguity. This was the machine flown by Captain Eaton. In the field of aviation archaeology, positive identification is usually the first step in a race against scrapping. Once a wreck is located, it typically becomes a target for unauthorized salvage. Aluminum is a valuable commodity. In accessible regions, crash sites are often stripped of their metal within months of discovery. Instruments are looted for souvenirs, and heavy structure is cut up for melt value. The Swamp Ghost avoided this fate through a combination of terrain denial and cultural enforcement. The physical inaccessibility of the Agaiambo swamp provided the primary layer of defense. The second layer was provided by the local population. The villagers living on the periphery of the wetland regarded the swamp as a forbidden zone. They believed the area was inhabited by malevolent spirits. This belief system acted as a highly effective security protocol. It created a psychological perimeter that prevented local scrapping operations. While the rest of the world forgot the plane existed, the local residents knew it was there but refused to touch it. This isolation preserved the integrity of the evidence. When a recovery assessment team finally inspected the site in 2006, they found a machine that was remarkably complete. The structural integrity was high. The fuselage had not been crushed by the vegetation. The wings remained attached to the roots. The rare Bendix ventral turret was still in position, hanging beneath the fuselage. This component is almost extinct in the aviation museum community because most were removed and scrapped during the war. Here it remained bolted to the airframe, protected by the same isolation that saved the rest of the airframe. The assessment also revealed the limits of preservation. Major aluminum structures remained sound, but magnesium and other dissimilar metal components had degraded severely, leaving fittings and moving parts seized, weakened, or missing. The verification of the site confirmed two critical facts. First, the aircraft was the specific airframe sought by the museum. Second, the airframe was strong enough to be moved. The main spars were not cracked. The transport splices were intact. The structure had settled, but it had not collapsed. This confirmation shifted the problem from investigation to engineering. The team now owned a verified 30-ton artifact sitting in the middle of a malaria-infested swamp. They knew exactly what it was, and they knew it was worth saving. The challenge was that the aircraft was one structure. To move it, they would have to reverse the manufacturing process. They would have to take it apart. The factory that built the B-17 assembled it with cranes and gantries on a dry concrete floor. The recovery team would have to disassemble it while standing in waist-deep water, utilizing floating rafts as their only workbench. The primary constraint governing the recovery of the Swamp Ghost was a simple ratio between gravity and lift. The aircraft in its resting configuration weighed approximately 30,000 pounds. There is no helicopter in the civilian inventory capable of lifting a complete B-17 bomber dead weight from a suction trap in a tropical environment. The physics of rotor lift in high humidity and high ambient temperature reduced the performance of any aerial platform. To move the object, the team had to reduce its mass. They had to break the aircraft down into component loads that fit within the safety margins of the available lift hardware. In May of 2006, a recovery team arrived at the Agaiambo swamp to execute this disassembly. They did not bring cutting torches. The objective was to preserve the aircraft as a museum artifact, not to reduce it to scrap. This requirement dictated a strategy known as production break disassembly. The Boeing engineers who designed the aircraft in the late 1930s anticipated the need for transport and repair. They built the bomber in major sections that were joined by high-strength bolts and terminal fittings. The wings were not welded to the fuselage. The tail was not cast as a single piece. The aircraft was a collection of sub-assemblies held together by fasteners. The recovery plan called for reversing the assembly line sequence. The team had to locate these factory production brakes and unbolt them. This sounds straightforward in a workshop manual, but in the swamp it was a severe physical challenge. The team could not stand on solid ground. They built floating platforms using timber and inflatable rafts to create a stable workspace around the aircraft. They worked in waist-deep water that was thick with organic sediment and concealed submerged snags. The first step was to strip the heavy, dense components that contributed the most to the gross weight. The B-17E mounts 4 radial engines. Each engine is a dense mass of steel and aluminum attached to the wing by engine mounts. The team rigged gantry frames on the floating rafts to support the weight of the engines. They disconnected the fuel lines, the oil lines, and the control cables. Then they unbolted the mounts. One by one, the 4 engines were lowered onto sleds and floated away from the airframe. This action significantly shifted the center of gravity and reduced the total load. The next phase involved the wings. The outer wing panels of the B-17 are joined to the inner wing sections at a specific breakpoint. The team accessed the internal structure and removed the rows of bolts that had been torqued tight in 1941. Despite the 6 decades of immersion, the anaerobic mud had preserved the threads. Many fasteners turned freely once the initial seizing torque was broken. The outer wings were slid off their spars and secured on the floating pallets. The most critical separation was the fuselage itself. The fuselage of a heavy bomber is a long, semi-monocoque tube. It is rigid, but it is susceptible to bending loads if not supported correctly. To reduce the lift weight, the team decided to separate the fuselage at the factory transport splice located just aft of the radio room. This would split the 60-foot tube into 2 manageable sections. As the team worked inside the fuselage to clear the internal lines and cables crossing this splice, they encountered the human evidence of the flight. Stowed in the crew racks, they found the original coffee thermoses still in position. They were not crushed or thrown loose. This small detail confirmed the callback to the soft field landing dynamics. The arrival had been so gentle that loose items remained on their shelves. These artifacts were tagged and removed to ensure they were not lost during the extraction. With the fuselage separated, the team faced the problem of lifting these fragile shells. A fuselage skin is designed to take aerodynamic loads distributed over its surface. It is not designed to be squeezed by a lifting strap. If a sling is wrapped around the aluminum skin and tightened, the crushing force will buckle the frames and ruin the artifact. To prevent this, the team utilized a technique known as spreader bar rigging. A spreader bar is a rigid steel beam that holds the lifting straps apart at a width greater than the object being lifted. This ensures that the straps hang vertically and apply force only in the upward direction. The team designed custom cradles that matched the curvature of the fuselage frames. The lifting straps were routed under these cradles so that the load was carried by the internal ribs and spars, not by the thin aluminum skin. Every section was rigged with this geometry in mind. The tail stabilizer was unbolted and crated. The dorsal fin was removed. The ball turret mechanism was secured. The aircraft was systematically transformed from a single 30-ton machine into a series of organized parcels floating on the surface of the swamp. The disassembly process took weeks of labor in high heat and humidity. The team battled dehydration and the constant difficulty of dropping tools into the bottomless mud. However, by adhering to the production break logic, they maintained the structural integrity of the story. They did not cut the spars, they did not saw through the skin. They simply undid the bolts that the factory workers had tightened 64 years earlier. The bomber was now packed and ready for flight. The final variable was the arrival of the machine that would pull it into the sky. The decision to extract the swamp ghost by air was not a stylistic preference. It was a topographic necessity. The geography of the Agaiambo swamp offered 0 viable surface routes. The water depth of 2 to 3 feet was too shallow for a commercial barge and too deep for a truck. There was no solid ground to build a temporary road. The only path out of the trap was vertical. This constraint forced the recovery team to select a specific class of lifting machine. A standard utility helicopter such as a Bell II-06 or an A-Star lacks the power to lift a heavy bomber fuselage. Their external load limits are measured in hundreds of pounds. The fuselage sections of the B-17, even when stripped of engines and tail surfaces, weighed thousands of pounds. The team required a heavy lift platform capable of operating in high tropical temperatures where air density reduces engine performance. They selected a Mi-8. This is a Russian-built transport helicopter originally designed for military and industrial applications. It is a rugged twin turbine machine known for its robust external sling capacity. In the logging and mining industries of Papua New Guinea, the Mi-8 is a standard tool for moving heavy equipment into inaccessible terrain. For this operation, it was the only aircraft available in the region with the muscle to move the B-17. The constraint was lift margin. A Mi-8 class platform is commonly sited around the 4,000 kilo class, but practical sling limits vary by variant and hot and high conditions, so the loads had to be broken down accordingly. If a fuselage section exceeded this weight, the helicopter would not be able to achieve a safe hover margin. The pilots would have to abort the lift or risk losing control. This weight limit validated the earlier decision to separate the fuselage at the production break. The forward fuselage section containing the cockpit and the radio room was the heaviest single component. If the team had attempted to lift the fuselage as one piece, it would have anchored the helicopter to the swamp. The extraction sequence began with the smaller components. The engines, the wing panels, and the tail stabilizers were rigged with the spreader bars described in the previous chapter. The helicopter arrived overhead, generating a massive rotor downwash that flattened the 10-foot-high kunai grass. The marsh water was whipped into a spray that coated everything in mud. The rigging crew on the floating rafts had to work blindly in this turbulence to connect the lifting loop to the helicopter cargo hook. When the helicopter took tension on the line, a new physical force came into play, the mud suction. The components were not just resting on the bottom, they were embedded. As the pilot applied collective pitch to increase lift, the cable went taut. The helicopter had to generate enough force to overcome gravity plus the static friction of the mud seal. The break was not instant, it required a sustained pull. Slowly, the suction failed and the aluminum sections broke free from the sediment bed. As the forward fuselage section rose from the water, a specific visual detail confirmed the history of the site. The aluminum skin displayed distinct horizontal discoloration lines. These were waterline corrosion marks. They documented the seasonal rise and fall of the swamp water over 64 years. The metal below the lines had been preserved by the constant immersion. The metal above the lines showed a different oxidation character from exposure to the humid air. This artifact was a geological gauge that was now suspended in the air. The pilot stabilized the load and transitioned to forward flight. The center of gravity shift on the helicopter was managed by the flight controls. The B-17, which had arrived in 1942 as a sleek aerodynamic form, departed in 2006 as a series of swinging pendulums. The helicopter flew the components to a staging area on the coast where a barge was waiting. One by one, the pieces of the swamp ghost were ferried out of the entrapment zone. Engines set down, wings stacked, fuselage sections cushioned on tires. The operation succeeded because rigging geometry controlled drop risk, production brakes controlled structural risk, and the Mi-8 controlled lift margin. With the airframe staged for shipment toward Leh, the remaining constraint was no longer physics but possession. The final flight of the B-17E serial number 412446 was a transit of roughly 40 miles from the interior wetland to the coastal port of Leh. This journey was conducted at the end of a cable suspended beneath the Mi-8 helicopter. While the weight of the segments had been managed by the disassembly plan, the movement of the aircraft through the air presented a final aerodynamic challenge known as heavy lift helicopter geometry. When a helicopter lifts a dense, compact load like a concrete block, the physics are stable. The load acts as a simple pendulum. However, a bomber fuselage is not a concrete block. It is a large hollow cylinder with significant surface area. It is an aerodynamic shape designed to fly at 200 miles per hour, but it is being dragged sideways and backwards at 60 knots. As the helicopter moves forward, the rotor downwash strikes the fuselage shell. This creates turbulent airflow that wraps around the aluminum skin. The fuselage tends to act as a wind vane. It wants to rotate and align itself with the airflow. If the load spins out of control, it can destabilize the helicopter, causing a catastrophic loss of control for the pilot. To prevent this, the recovery team had to ensure the sling geometry included stabilization features. They often used drogue chutes or specific rigging angles to force the load to fly straight. The pilot in the Mi-8 had to constantly manage the cyclic control to counteract the swinging momentum of the 30-foot-long fuselage sections. The aircraft survived this chaotic transit. The helicopter deposited the disassembled bomber at the coastal staging area, where the components were loaded onto a barge for Leh. The extraction phase was complete. However, upon arrival in Leh, the operation hit a barrier that was harder than the Agaiambo mud. The government of Papua New Guinea intervened. The Public Accounts Committee raised questions regarding the legality of the export permit and the agreed compensation for the national heritage item. The aircraft was seized. The containers holding the dismantled sections were impounded at the wharf. For the next 4 years, the B-17 remained a prisoner of a legal dispute. This delay introduced a new risk profile. For 64 years, the aircraft had been preserved by the anaerobic freshwater mud. Now it was sitting in a shipping container in a coastal industrial zone exposed to the saline humidity of the Bismarck Sea. The environment had shifted from a preservation zone to a corrosion zone. The team could not access the artifact to apply conservation treatments. They could only wait while the political and legal process ground through the courts. During this interval, the aircraft drew international media attention under the nickname Swamp Ghost, a label coined after the 1972 rediscovery, not by the wartime crew. In engineering terms, it was not a ghost at all, but an impounded artifact caught in a dispute over ownership and heritage. In 2010, the political deadlock broke. The government cleared the aircraft for export. The containers were loaded onto a ship bound for the United States. The aircraft arrived at the port of Long Beach and was eventually transferred to the Pearl Harbor Aviation Museum in Honolulu, Hawaii. The outcome of the recovery is classified as a success, but it is a qualified success defined by the constraints of the method. The aircraft was not restored to flight status. It was not polished to a mere finish. The museum made a curatorial decision to display the aircraft in a state of arrested decay. They reassembled the major components, but they did not hide the scars. The fuselage still bears the waterline marks from the swamp. The lower surfaces are still stained by the organic tannins of the mud. The bent propellers remain bent. The missing magnesium fittings are not replaced with modern replicas. The aircraft is presented exactly as it was found, but stabilized to prevent further deterioration. This approach validates the logic of the production brake disassembly. Because the team unbolted the aircraft rather than cutting it, the reassembly at the museum was precise. The wings were mated to the fuselage using the original bolt holes. The tail was reattached at the original station lines. If the team had used cutting torches to slash the airframe into manageable chunks, the reconstruction would have required heavy welding and patching, which destroys historical integrity. The B-17E 412446 is now a static document. It proves the reality of the Rabaul mission in February 1942. It proves the survival of the crew. It proves the preserving power of the Agaiambo swamp. The gap between the loss and the recovery was 64 years. The gap between the recovery and the display was 4 years. The timeline is now closed. The machine is no longer waiting in the kunai grass. It is secure on a concrete floor, serving as a permanent witness to the engineering and the endurance of its era.